Okay, we'll go ahead and get started. Welcome everyone to the Uncrewed seminar, and I'm pleased to welcome Adam Houston. Adam is a professor of atmospheric science at the University of Nebraska-Lincoln. He earned his BS in meteorology from Texas A&M and his PhD in atmospheric sciences from the University of Illinois at Urbana-Champaign. He served as a visiting assistant professor and postdoctoral research at Purdue before starting at the University of Nebraska-Lincoln. Welcome.
It's working? Okay. Okay, good afternoon. Thanks for joining us. I'm happy to be back at NCAR. It's been a few years since I've been here, but thanks to Gretchen and Hugh for the invitation. So I'll launch into it because I'll tell you from the outset, this is a kind of an overview of the work that I've been doing over the last many years. So much like the Platte River, it's very wide, but not very deep. So if you have any questions, I'm happy to dive into it, but it's gonna be kind of superficial. There'll be some meat on the bone, but not a lot. But first, I have to thank the many people who've contributed to this. First and foremost, my students, one of whom is in here, who led a lot of the research that I'm going to present, and I will acknowledge them as we go. And then a ton of collaborators at multiple institutions. I'll pick a few because Brian and Eric at the University of Colorado were kind of the incubators for some of the initial efforts that we took on. But there are a lot here, and I'm grateful for all of them. I'll call some of them out as I move forward. So just a quick kind of outline of what I'm going to do. I'll talk a little bit about what an uncrewed aircraft system is, though I think I don't need to dig into that too deeply, but to make sure we're on the same page. Talk a little bit about why we use UAS for studying severe local storms, SLS. Talk a little bit about the applications of UAS for SLS research, and then the application of UAS for forecasting. I will spend a bit of time on that. So let's talk a little bit about what UAS are. They've gone by a number of names over the years. Unmanned aircraft system, uncrewed is the term we typically use now. UAV, remotely piloted vehicle. I mean, so there's lots of different terms. But I want to get kind of away from the terminology and talk really about the functionality. Because there are two different classes of UAS that are often used. And I think a lot of people, when we say UAS, think of a rotorcraft, the rotary wing drone. You can see two over here that we've used. And those probably make up a majority, I'd say, of the platforms that are used, but there are also fixed wing, and a lot of the work that I'm going to show today is based on fixed wing drones. And the distinction is important because generally speaking, rotary wing drones are easier to operate. I can operate it, I don't typically crash them. They are more limited though in how they operate. So they typically only do vertical profiles. Now they can move horizontally, of course, but they often have lifetimes in the order of 30 minutes. And so you're limited in how far you can go horizontally. Fixed wing, on the other hand, much more difficult to operate. I crash mine all the time, my toy one, not for research. They're much harder to operate, but they have a lot more versatility. So the Raven, which we'll talk about, I'll talk about that extensively today, has a flight time north of 2 hours, so 2.5 hours. It gives you a lot more flexibility in how you operate. And so most of the horizontal transects you would want to do, crossing certain features, are done with fixed wing. Okay, they've been used for atmospheric science for many years, so I'm certainly not the first, and I'm not going to be the last, hopefully, who have used this. Just a couple examples. This is from Taurus, but they've been used in the Arctic. National Severe Storms Lab has used them for surveying. Melissa has done some of that work. This is a rotorcraft here that we used during lapse rate in the San Luis Valley of southern Colorado. So they've been used quite often for atmospheric research. But let me talk a little bit about why you would use UAS specifically for severe local storm research. And ultimately what we need for severe local storms research are meso-gamma scale observations. And we use them to improve conceptual models of severe local storms. And I realize some of this is obvious, but I just want to make sure we understand how UAS fit into this, the problems that we're trying to solve kind of writ large. And we also, and this is important because we want to relate the operationally mostly observable meso-beta scale, so the larger scale, 20 to 200 kilometer scale phenomena. And I say mostly, and I'll talk about that in a minute, but they're mostly represented in the operational nationwide network of observations. Those environmental conditions to the operationally unobservable meso-gamma scale. So we shouldn't expect that we're going to get in situ observations at the meso-gamma scale on a regular basis, at least not in the near future. And so to improve the conceptual models, we need these small scale observations, but to relate them back to the larger scale observations that we can make on a regular basis, we need to be able to make that connection. Okay, so if we look at the typical distribution of surface observations across the country, this is what it often looks like, or typically looks like. And so what we could say is, yeah, maybe you could get meso-gamma scale structures with this kind of density, particularly on the East Coast. You certainly can get meso-beta scale, 20 to 200 kilometer with this kind of resolution, these kind of observations. So just kind of under the assumption that we need both of those, we need meso-gamma and meso-beta scale, the surface observations kind of get close. But if we go just 500 meters above the surface, the network gets very coarse, very sparse. And so most of these are based on radiosondes, which obviously are only released twice a day, so this gets even thinner if we're removing radiosondes. The rest of them are commercial aircraft that are landing and launching, taking off from main airports. There are a few LiDARs scattered about. The vertical wind profiles from ADADs contribute kinematic, but clearly the message is there's just not much at this level. Now one could say, why do we need observations at 500 meters? We have them at the surface, we can infer what's happening in the PBL if we have surface observations. Sometimes you can't. I mean, I see people smirking. Sometimes you really can't, and it's when we can't do that that often we need them the most. That is, we need those observations above the surface to really close those gaps. And this is called the lower atmosphere in situ data gap. We just do not have data basically between 10 meters and about 5,000 meters. Now, commercial aircraft, if I showed 5,000 meters, we'd see, or even higher, 10,000, we'd see a lot more coverage because commercial aircraft are spending time in that part of the airspace. But it's this gap, this lower atmosphere gap, that becomes particularly important. And I'll show you an example here in this talk of one situation where that was potentially important, but there are many others. Okay, so conventional observations are insufficient for research if you're looking at meso-gamma scale, okay? Now, ADADs are great, they get high resolution, but you're not gonna get thermo, right? And you can get reflectivity and they're fantastic, but if we're looking at thermodynamics and three-dimensional kinematics, we can't get that at the meso-gamma scale with operational network. Conventional observations. Conventional observations above the surface within the PBL are even insufficient for representing meso-beta scale. So we have two problems. We don't see the meso-gamma scale. In some ways, we don't even see the meso-beta scale, so it's hard to close, to make improved conceptual models, and it's hard to close this gap between the meso-beta and meso-gamma. So we can't make those theoretical connections between the meso-gamma scale and the meso-beta scale because we don't have either observations. And even if we had these connections, it's very difficult to apply them operationally. Okay, so what can UAS do? Number one, they have the capability to do targeted and flexible operations, and when and where the data are needed, so we can theoretically put them where they need to go to collect those observations. And we can think about this in terms of research, we can think about this in terms of augmenting the conventional observations. Either way, they are flexible and targeted. So we can get above surface transects in or near storms. I mean, obviously storms are important if we're thinking about SLS applications. High fidelity in situ profiling, so high fidelity meaning both in time and space. We can get simultaneous and rapidly repeatable data collection in multiple areas. So just a few UAS can map out a very large space, particularly if we have flight times that are on the order of several hours. And it's controlled. So there have been many uses of swarm sondes where we release small balloons with sondes and they go into features like storms and they create great mappings of in situ kinematic fields. We have no control over them. So if we're trying to target specific features, that becomes nearly impossible with that type of platform. And so, ultimately, we can use them to advance understanding of meso-gamma scale structures and processes. We can connect the meso-beta scale with the meso-gamma scale, and we can resolve meso-beta scale above the surface. So we kind of check all those boxes in theory with this platform. Okay, so let me talk about some specific applications of UAS for severe local storms research. And I'm gonna start with Vortex 2. There was a project back in 2009 called COCONU that Brian Argo, Eric Frew, and I led. I'm not going to talk a lot about that because that led to this. And Vortex 2 back in 2009, 2010 was a very ambitious field campaign UAS were just a small bit of it. Most of it was mobile mesonettes and mobile radars, but we were funded to basically prove a concept. Can we use drones to get into storms and collect data? And it was only a 2-year award, whereas most of the Vortex 2 proposals, grants were allowed for analysis and post-processing. This was basically, can you do what you were saying you can do? And so the major accomplishments weren't necessarily science objectives, it was just doing it. It was getting the authorization from the FAA, and all those little boxes represent where we had authorization to operate. It's a fairly narrow part of the US, but we actually were able to get that authorization. We also had the first intercept of a supercell by a UAS back in 2010, and the first sampling of an RFD. So most of the major accomplishments weren't big science objectives, they were just proving that we could do it. But we did do a little bit of science with it, and I'm gonna emphasize this one paper, this was one of my students, Curtis Riganti. So we looked at the last chance case. This was in June of 2010. This is the supercell that we targeted. A couple of boundaries indicated this is the rear flank gust front. This is the rear flank internal surge boundary, so a surge of momentum back within the outflow on the rear flank. And this is the reflectivity field. 3 different air masses indicated, and these are, they're not labeled here, but essentially A is the inflow, B is this cooler air within the outflow, and then C is this air kind of in the, sorry, missed that up. Yeah, C is this air behind the surge. And so all of this should be outflow air, should be just the cool, perhaps moist air, but that's been driven by the formation of the rear flank downdraft. But what's interesting is if you look at the potential temperature, you'll notice the inflow air appears to be found within the outflow. And so what we've seen here, this is a transect that we flew with a single aircraft, conceptualization of what we saw. You have the kind of a classic density current with this turbulent wake behind the outflow head, which essentially brought in both inflow momentum and inflow temperature and moisture conditions. And this is not, I mean, the existence of these kinds of features is not unknown, but the presence of them in supercells hadn't been shown with this kind of fidelity. And so, kind of cool that we saw something like this, but it also potentially offered an alternative explanation for rear flank internal surges. So this is that surge, we pass into it as much colder, but what we hypothesized is that perhaps the advection of this momentum from the inflow actually produced through kinematic phreноgenesis this boundary. And so essentially the boundary in and of itself wouldn't have existed without this turbulence in the wake behind the outflow head. Okay, so we're able to do a little bit of research, a little bit of science with these data. But again, the primary objective and the primary accomplishment of Vortex 2, at least our participation in it, was proving that we could do it. But Vortex 2 led to a much more ambitious project that was more centrally focused on UAS, and that was Taurus. So Taurus was, as a lot of these are, involved multiple people. So myself, Chris Weiss at Texas Tech, Conrad Ziegler, Eric Rasmussen, Mike Coniglio, Brian Argro, Eric Frew, all of us were the PIs for this project. And so it involved UAS, obviously I'm gonna talk about that, but it also involved mobile radars, mobile mesonettes. The P3 was involved in 2019 and 2022. So a multi-instrument kind of campaign. Now, it was broken into 3 years, 2019, 2022. Obviously, pandemic was in between there. These were the first 2 years, and then we got additional funding to conduct Taurus Light in 2023. UAS were used in 2019 and 2023. So let me talk a little bit about the aircraft we used. You'll see this video here. This is the mechanism that we used to launch the Raven. This kind of was a game changer because in the past what we would do is we would take this bungee cord, this elastic band, and we'd anchor it in the ground and we'd pull it back and we'd put the aircraft on the ground and then the wind shift would shift and so we'd have to move everything. It was just a very cumbersome process. This is much more flexible. So Steve Bornstein actually developed that at CU. But so Raven is a 91-inch wingspan aircraft. It's obviously fixed wing. The instrumentation, I could drill into that, but basically we're collecting typical state variables: temperature, humidity, pressure, and wind. The way we did temperature was a little bit different in 2023, but the basic state variables we're collecting didn't change. The primary objective of Taurus, kind of the whole project, not just what UAS were aiming to focus on, was to determine the relationship between storm-generated air mass boundaries and coherent structures within the supercell outflow to the generation and amplification of near-surface rotation. It's kind of a mouthful, but essentially, we know that these features exist within supercells, these coherent features. We're trying to relate those back to the amplification of near-surface rotation. Now, you don't see tornado in the description here, but essentially, if you can amplify the rotation of the surface, then other processes can then result in tornadogenesis. We were not focusing on tornadogenesis per se, because that's a process that is very small scale, but we were looking at how we could get surface rotation to be amplified through these features. And there are lots of features. We were focusing on the left flank convergence boundary, forward flank convergence boundary, this vorticity river, and these are simulations. So a lot of this that motivated Torus was based on simulations. We needed observations to test some of these hypotheses. Rear flank internal surge boundaries, rear flank, the rear flank gust front, forward flank gust front, and the SVC, which is this feature that often develops in the left and forward flank of a storm that is above the surface, and that animation from Lee Orff's work, let me see if I get that running again, is a good illustration. It's essentially this tube of vorticity on the forward flank that is ingested into the storm and has hypothesized to amplify the ascent above near surface rotation, and therefore through convergence, amplify the near surface rotation. But the point is we're trying to characterize these features but relate them back to the generation of near surface rotation. We also wanted to look at how storms actually modify their own inflow. This is a focus that Mike Caniglio led, and because that feedback could be important. We had two secondary objectives. We basically were developing and evaluating real-time provisioning of targeted mesoscale observations to the National Weather Service forecast. So with the data that we were collecting during Torus, we were distributing in real time to the National Weather Service. And then finally, and I will talk more about this later on, we tested the assimilation of Torus data into storm scale numerical weather prediction models. Kind of a brief summary of what we did during Torus. We had 43 total deployment days, 46 supercells, 16 of these were tornadic. It's a pretty good ratio. A lot of these were pretty weak tornadoes. A lot of soundings, a lot of swarm sondes, a bunch of time with the P3 and quite a bit of time with UAS. Again, this is across 3 years. 2 of those years were ones with UAS. Okay, so I'm gonna talk a bit more about a specific project that we were doing with these data that leaned heavily on the UAS data. So this is a project led by Mark DeBryan, one of my grad students. He recently graduated. The paper is currently in review. So we took 3 cases from Torus and Torus Light, and we wanted to address the following. We wanted to try to answer these questions. Is the 3D structure of the sampled boundaries best described by a convergent boundary or a gust front / density current? Now, on its surface, it sounds like a very academic kind of question. Who cares what we call it? The reason this is important is because the gust front / density current characterization connects the structure of that feature to the environment much more cleanly than a convergence boundary. We know pretty well how density currents respond to the vertical shear, for example, or the source of cold air. We know that if the vertical shear in the opposite direction of the density gradient is large, the ascent and depth of the density current is also large. So if we can make those kinds of connections, then the features that we see on these gust fronts are more cleanly associated with the environment. But if they turn out to be convergence boundaries, this connection starts to weaken. And so our conceptualization of the role that these boundaries play in supercells is more cleanly illustrated if we can show that they're density currents. And if we can't, it opens up more questions. What does a convergence boundary look like under varying vertical shear and other environmental characteristics? Second of all, we wanted to look at how vorticity is maximized near these boundaries. Is it maximized in the cool air? Is it maximized in the warm air just ahead of the boundary? Is it maximized to the surface? Is it maximized aloft? And answering this question gets us closer to, though it doesn't actually tell us necessarily, what the fundamental mechanism is for this vorticity. What's actually generating this vorticity? There's this theory that was developed by Bob Davies-Jones and Harold Brooks that we call kind of euphemistically the feet first tilting mechanism, but essentially it's a mechanism that relies heavily on horizontal vorticity generated baroclinically. And that process requires baroclinic gradients. It requires density gradients in the horizontal. It requires more than that, but answering this question gets us closer to the fundamental mechanism causing it. And the other things we want to look at is, do we actually see ascent of cold pool air? This seems like kind of a minor thing. I mean, why would you not see that? Well, it's stable, so cold pool air shouldn't normally ascend. But indicating that, seeing that, is also getting us closer to which mechanism is actually driving the generation of vorticity. And the other thing, the last bit that we want to look at is how much of the horizontal vorticity that we see across these boundaries is driven by the vertical motion gradients. So we all know horizontal vorticity has two components. One is the lateral gradient and vertical motion. The other is the vertical gradient and horizontal motion. This is an example of the diagnosis of horizontal vorticity, all these colors here, using RHIs from a radar. So the radar scanning at RHI, they're looking at the horizontal winds and essentially the vertical shear contribution to the horizontal vorticity. Makes a lot of sense. You can get really high resolution results. But it's completely ignoring the horizontal gradients and vertical motion. So how much of the actual horizontal vorticity that we see in these storms exist in the lateral gradients in W? And therefore, how much are we actually missing in this diagnosis based on vertical shear alone? Okay, so we looked at these three cases. I'm not going to talk about all three cases. In fact, I'm only going to talk about one case and actually one transect from this one case. This is May 26th of 2023. This was in, as almost all cases were in 2023, in West Texas, eastern New Mexico. This is the storm from 80 AD, kind of looks like a blob, but this is where we were. So we're just to the east of the meso. The velocity, radial velocity on the right's from the Ka band radar, so you see a little bit more detail. Okay, there's a lot going on here, so let me kind of step you through what we have. These are all cross-sections, and they're cross-sections developed using the two Ravens that were flying aloft and a mesonet, mobile mesonet that was at the surface. So these are the paths of these platforms. And from these platforms, we developed an approximation through a time to space correction, this 2D plot. Okay, so this is perturbation, virtual potential temperature, perturbation based on some reference on the upstream. And you see some really familiar structures. You see the outflow very clearly. You also see multiple boundaries, and not just in the theta V field, but in some of these other fields. But there are multiple boundaries here, and the spacing between these is not large. I mean, less than 1 kilometer in some cases between these surges. This is structure that we have not really seen because we never had the fidelity before, particularly aloft. Theta E, you kind of see the same structure. What's popping out here is it kind of looks like a density current. I mean, if I had no other information, I'd say, that's a density current. Looks like a density current. But the problem is that the pressure is not consistent. These colors are actually negative pressure perturbations. So the pressure is actually lower back in here. And you don't even really see much of a positive pressure perturbation that you would expect with a classic density current. It's very odd, but it's not inconsistent with some of the surface observations we've seen through StickNet and mobile mesonet. But now we see more than just a surface-based measurement, more of a 2D confirmation of this. And again, this is just one case, but we're still seeing that lack of a pressure signal that you would otherwise expect with a density current. We see vorticity and divergence as well. I'll focus a bit on the vorticity because the largest vorticity, these purple colors here, are behind the lead boundary. So we're not seeing them on the front edge, we're seeing them in the cold air. We also see this spike in vertical vorticity near the surface associated with this convergence boundary, which is interesting because this internal convergence boundary appears to be, our hypothesis is, driven by the SVC. That SVC is, remember, that horizontal tube of vorticity is primarily aloft. It's actually driving, in our hypothesis, the formation of this convergence boundary, which is then converging vorticity and creating that vortex sheet. This is a feedback between the SVC and the surface that we have not seen before, which is kind of interesting. It's one case, but it is an interesting connection. Okay, so the takeaways, multiple surges. This was not just a simple, what we call 3-boundary model. There are multiple boundaries indicated, and some of these very closely spaced, and some of these are tied to important features, the existence of strong vertical vorticity at the surface, for example. So this 3-boundary model that kind of has served as our conceptualization of the boundaries within supercells probably needs to be relaxed in some way. All three cases, and I obviously didn't talk about two of them, showed evidence of this feet-first tilting mechanism, this Davies-Jones and Brooks mechanism. And also, and I didn't show the results from it, but the singular Doppler RHI-based estimates of horizontal vorticity underestimated, and sometimes significantly underestimated, the magnitude of horizontal vorticity because it was missing the lateral gradients in W. Okay, another case I want to talk about is from 2019, 28th of May. This is work led by Kristen Axon, one of my grad students years ago. Paper is out, came out in 24. We're using, again, a collection of platforms. This is the P3, this X-wing looking thing. And these are all the observation or platforms during this case. Two storms. The Tipton storm is a southern storm. It produced an EF2 tornado near Tipton, Kansas. This one, which looks like a really strong supercell, produced no tornado. So obviously there's a question here. Why is one producing a tornado, the other one not? If you look at the environment, it's very obvious why this is producing supercells, and we had 27 meters per second of 0 to 6 kilometer bulk wind differential, clearly going to support a supercell. But if you notice the low-level SRH, 0 to 1 SRH is really small. Ordinarily, we would expect that to not be supportive of tornadoes, but this one produced not only a tornado, but an EF2. And the reason we suppose, we're hypothesized based on our analysis, is that the Tipton storm, not this northern storm, was ingesting a different air mass. And there's this air mass here, it's obviously in cartoon form here, but this air mass is what we call a mesoscale air mass with high theta E. And so the characteristics of this air mass primarily are twofold. One, the theta E in this small region is higher than anywhere else. Number two, the winds are backed. So whereas the flow in the warm sector is from the south-southwest, the winds in the mat are from the northeast. So you have elongated the hodograph, you've potentially increased the CAPE. This mat, this thing we've called a mat, it's based on some work that one of my students and I did years ago. Mats have been observed in the past. We weren't the first to observe it. We were the first to actually do a set of simulations to codify some of the mechanisms that we think are forming mats, at least one of the mechanisms. So I'm not going to talk too much about this, but I wanted to give a nod to Wolfgang's work because this really showed what a mat was. But again, the characteristics are it's small scale. This is fairly narrow, 15, 20, 30 kilometers, higher theta E than in the warm sector, and generally backed winds. Okay, so what are the implications? Well, if you have higher theta E, you would expect larger CAPE. If we look at the two environments, so we have the warm sector and then within the mat, the CAPE is actually pretty similar. I mean, basically not statistically significantly different. Basically the same, and I'll explain why it's pretty much the same. But what's most important is that within this mat air mass, the SRH is a lot larger, I mean, almost an order of magnitude larger. So we have a lot more SRH, a lot more potential, at least kinematically, for tornadoes, and the CAPE was about the same. What's interesting about this far right panel shows the vertical profile of theta E within the mat, so that's the red line, and then in the warm sector. And you notice that in the lowest levels, it's actually lower theta E in the mat than in the warm sector. And part of the reason for this is because we had an anvil that decoupled the atmosphere just ahead of the boundary. But so essentially the mat only manifested above the surface. So if we imagine that we only had access to surface data, this mat would have not shown up. We had had no information that the mat existed. This is one of those examples, and again, there are many of them, where you need data above the surface. Knowing what's happening at the surface is not telling you what's happening aloft. We'd have completely missed the presence of this mat. But the presence of this mat essentially is what we hypothesized was the difference between the Tipton storm producing an EF2, whereas the storm farther north, which didn't have access to that air mass, did not. And just ahead of the storm, the mat would not even have been identified if you had only surface observations to rely on. Okay, so I'm gonna pivot, get a drink of water. Okay, so this is not Taurus, this is SCALES, a fairly recent project, 2024. SCALES stands for Small UAS Coordination for Atmospheric Low-Level Environmental Sampling. I don't think I've ever been able to do that from memory, so I have to read it. It's a great acronym, and the reason it's great is because SCALES is broken into two subcomponents. mesoscales, and microscales. I take no credit for this. Elizabeth Smith gets full credit for that. So this was a project that Elizabeth Smith, myself, and James Pinto led, along with Tyler and Gus at OU and OSU. And so the project had a focus in eastern Oklahoma. So these are the positions of all of the UAS that we had distributed across eastern Oklahoma. You can see Oklahoma City and Tulsa. You'll notice a concentration around Tulsa. So mesoscales was kind of the larger scale distribution of UAS, mainly focused on testing the 3D mesonet concept, something that Phil Chilson put forward years ago. The microscales, which James and I led, was focused, again, right around Tulsa. This is the piece that I led, the microscales UHI domain. So this is focused on urban heat islands, UHI. You can see the distribution of assets within Tulsa. You can kind of see where Tulsa is. You'll notice these circles here. This is controlled airspace, Class C and Class D airspace. That's important because we actually had to fly into Class C airspace as part of this project. So being able to get authorization to do that was an accomplishment. Okay, but the focus of the microscales UHI bit was to characterize the 4D impacts of urbanization on deep convective environments. So are thunderstorms more or less likely in or near urban environments? Now, there's been plenty of evidence to suggest that precipitation tends to be larger downstream of urban areas. We did some work where we showed that deep convection initiation points tend to be more prolific downstream of urban areas. So there is evidence that something is happening with an urban area. But we really wanted to ask the question, what is the thermodynamics? What do the thermodynamics look like in an urban area versus a rural area? And so we took all these data and we plotted them in a time height framework. Now, all of these are perturbations. This is potential temperature, and I'll explain the different panels in a minute. Potential temperature, mixing ratio. And so the warm colors indicate a positive perturbation relative to upstream sites. So all of these are relative to these upstream sites. So essentially, if it's a positive perturbation, it's larger than those upstream. And what we see is, sure enough, in the urban sites, let me show you the urban. So this one, the urban compact high-rise site, is that site right there, kind of in the downtown district of Tulsa. This second panel is the downstream 5 kilometers, so it's 5 kilometers downstream. It's not all those sites, only one of those is activated each day, but it's downstream 5 kilometers. And these two are composites, an urban composite and a plume composite. And the takeaway is that it's an urban heat island. It looks like one. We have positive potential temperature and negative mixing ratio. In other words, it's warmer and drier in the urban areas. And it shows up as a statistically significant signal when you consider the urban composite. You even kind of see this in the plume downstream of the urban area as well. So there's some suggestion that this urban heat island, as we would expect, is advected downstream. The other thing to note is the height of the planetary boundary layer. So this continuous curve here is the height of the planetary boundary layer at the particular site. So this is the urban site, and that is the upstream site. So we see that the depth of the planetary boundary layer is deeper. Again, not surprising. Nothing here is that revolutionary, but it is showing that we do see an urban heat island and the expected response in the PBL depth. What we wanted to do, though, was go a bit further and say, how does this impact the instability, the potential energy that might be available for storms? The problem is that on these days, there was hardly any CAPE. So we can't use CAPE. We'd love to use CAPE, but there wasn't any CAPE. So we had to come up with a different mechanism. And in reality, it tells us the same thing. It's the total potential energy. And so it's very much like CAPE, except that it's integrated from the surface up to 2 kilometers above the LCL. And so essentially, it's the total amount of buoyancy, both negative and positive, integrated from the surface up. And so we'll capture some of the unsaturated absolute instability that we might see in the PBL, as well as any potential conditional instability associated with saturated ascent above the LCL. And what we see is that almost without exception, focusing on these panels, this panel here, the urban areas had less total potential energy. So in other words, they were less favorable for thunderstorms than non-urban areas, which seems kind of strange. If thunderstorms precipitation tends to form more readily downstream of urban areas, why are we seeing, in this 1 week, less total potential energy? I mean, in some ways, what we can take away from this is that the absence of moisture is winning. Right, so we have more temperature, higher temperatures, but the absence of moisture is making for less total potential energy. But that's not the only thing going on. Notice that, as I already said, that the depth of the PBL was higher for the urban areas than in the rural areas, where there has been some suggestion. Jake Mulholland and co-authors showed that the depth of the LCL scales with the size of the thermals coming out of the PBL. So if the LCL is deeper, maybe the thermals in urban areas are larger. And if the thermals are larger, maybe they are more likely to overcome the dilution that would otherwise prevent them from becoming deep. Moreover, if we have more instability in the lowest levels of the atmosphere, perhaps our interest isn't so much in what's happening above the LFC or above the LCL, but how much energy is being imparted in the lowest part of the atmosphere. That is, how much vertical velocity is coming out of the PBL, not just how big the thermals are, but how fast they're coming out of the PBL. So the bottom line here is that we probably need to move beyond just the thermodynamic CAPE-driven focus on these environments and look at more of the structures within the PBL. Okay, so that's all on the research aspect of this. I want to pivot into how we're using UAS to evaluate the potential impact on forecasting. And there are many ways that we can envision UAS being injected into the conventional observation network. We can have fixed-wing aircraft at WFOs that then are scrambled into areas where we need them. We can have kind of the 3D mesonet concept where they're just constantly profiling, not constantly, but instead of just having the surface-based mesonet, a three-dimensional mesonet, maybe augmented by fixed-wing that are doing transects across interesting features. Maybe we could put radars on them. Maybe we can drop SONs from them. And there's all kinds of ways we can envision how we would do this. But the point is that regardless of how we envision it, we need to answer a pretty fundamental question. What do forecasters actually need? We don't want to be telling forecasters what they need. They need to tell us what they need. And how might UAS data improve this? How might we use these UAS to fill in any gaps? And this goes not just to giving the data directly to the forecasters, but how might they improve numerical weather prediction? Okay, so we conducted this survey, and I'm going to go through this kind of quickly, but it is really important, I think, that asking this question: what phenomena do you find as a forecaster difficult to forecast because of data gaps? Not just because they're necessarily intrinsically difficult to forecast, but which ones are made more difficult because of data gaps? What characteristics need to be observed to fill these data gaps, and what role might UAS play in filling these gaps? And this was a work funded by the Cloud Map effort through NSF. Okay, so you probably don't need to pay much attention to this. This was in this paper that came out in 2021. I'm going to focus kind of on the right panel here. So we basically said, using somewhat some arbitrary thresholds, was a particular phenomenon difficult to forecast or not difficult to forecast? And if it has a green check mark, it means it was difficult to forecast because of data gaps. So anything with a green check mark means it's a challenging forecast phenomenon because of data gaps. We also broke it down into forecasters, everyone, but also those forecasters that say they forecasted this particular phenomena frequently. We felt like that was something that we needed to know. If someone is typically forecasting floods and finds it difficult because of data gaps, I think we give them a little bit more credence in our evaluation. Bottom line, floods are difficult to forecast because of data gaps. Severe thunderstorms, not that they're not difficult to forecast, but they didn't either rise to the level of being difficult or be low enough to be not difficult to forecast. So they're kind of in the middle, which I thought was kind of surprising, frankly. What was also surprising for someone who focuses almost exclusively on warm weather phenomena is the precedence of cold season phenomena. A lot of cold season phenomena were difficult to forecast because of data gaps. This has nothing to do with UAS, right? This is just setting the frame. They basically find that forecasting winter weather phenomena is exceedingly difficult because of data gaps. And this shows up in other things when we ask them about the specific characteristics that need to be represented. Again, winter weather, temperature profile and mixed precipitation, hydrometeor type in winter. I mean, winter weather is a problem. Radar gaps is third. I mean, we should expect to see radar gaps somewhere on here. I was a little surprised that it was as low, but still, it's top 3. So, but there are some warm season things, near storm vertical wind profiles, wind shear, the pre-convective environment. But the message that was just resounding was how hard it is to forecast winter weather because of these data gaps. And the last question we asked was, how might UAS be used to fill these gaps? Asked a bunch of different questions, some that I found interesting. National Weather Service forecasters do not care how the public view the use of these platforms, which I love. I mean, I understand that it may be a bit myopic, but they don't care. They want the data. They want good data regardless of what the public views as the value or the threat. They also really like the idea of it being on demand or short notice, as opposed to fixed site stations. Now, this maybe shouldn't be surprising because the beauty of a UAS is that it can target, that it can go to where data are needed, but they really did embrace that. And this kind of came out in this. We asked the typical operation mode that they thought might be the most useful. Targeted surveillance, transects between sites, or just fixed site profiling, and they really leaned on the targeted surveillance aspect of it. Not to say that those shouldn't be, but they really leaned into that potential capability of UAS. Okay, so basically a summary of what I just said. Winter weather is important. Radar gaps are there, not top priority, but important. And the on-demand short notice capabilities, possibly facilitated through targeted observations, is something they feel is important. Okay, so there is a need. UAS may play a role or could play a role in filling it. But remember that another aspect, of course, of forecasting is improving numerical weather prediction. And so how might UAS be used to improve numerical weather prediction? Now, in theory, UAS data collected could improve numerical weather prediction. And I specifically say through severe local storms, but just in generally through assimilation of targeted observations. So you fly drones into areas that we need data. We assimilate those. We could assimilate surveillance, so the kind of the 3D mesonet idea. We're just constantly profiling, assimilating those data. And another, which I'm not going to focus on here, is ensemble subsetting or weighting. You could take observations between data assimilation cycles and use those to subset or weight an ensemble. Again, I'm not going to focus on those. I'm going to really focus on these first two. Okay, so this gets to Matt's work. He did a 2-part study for his PhD where he looked at this particular case, 8 June 2019. The first part was to examine what was really causing the behavior that we saw. And the behavior that was interesting is that we had 2 supercells. The first supercell was at the beginning of this animation. This is the second supercell. And the reason this is interesting is because the first supercell died after 30 minutes or so. The second supercell lasted for several hours and went on to produce a weak tornado. So very different behavior. And so one of the first things he looked at was, what is the explanation for that behavior? I won't talk too much about what he found, he can tell you, but I will talk to you about what we found when he assimilated these data into a numerical weather prediction forecast model. And we used a model very similar to the Warnine forecasting system. It wasn't exactly like it, but it was that kind of model. So 3-kilometer grid, a pretty rapid cycling, and using a DART for the data assimilation. And so it's important to keep in mind, and this is really important from the outset, TORUS was not designed as a primary objective to collect data to improve numerical weather prediction. It was designed to collect data in the storm to answer fundamental questions. And the reason that's important is because we're going to throw these data into a numerical weather prediction model and see what happens. And spoiler, it does improve the model. But they weren't even designed to do that. We weren't even collecting data in a deliberate way to improve numerical weather prediction. It just so happened that the data that we're collecting to improve our understanding of supercells happened to improve the forecast. There is a better way to do this. We could actually be intentional about how we operate a platform to do this. But this was kind of a first foray into this idea. And it really was. It was the first time someone had done something like this, where we assimilate data collected in a near storm into a numerical weather prediction model. And so the way we did this is a data denial framework. So essentially, you assimilate all the data, conventional obs and radar, no supplemental data. And then you assimilate all the data. This includes the conventional plus all of the other data that were collected during torus. And then you systematically exclude one set of data. And the way we did this is we broke the atmosphere into layers, surface, PBL, and free atmosphere, and asking the question, which of these layers had the biggest impact on the forecast? And subsequent data, which I won't talk about here, subsequent analysis by another one of my students, really focusing a bit more on UAS. This is focused mainly on the layers. And so in this PBL, it could be UAS, it could be radiosondes that were launched within the PBL. Free atmosphere is almost exclusively radiosondes, and the surface is almost exclusively mobile mesonettes. Okay, so the takeaway, it does make an impact. These 4 panels are forecasts that were initialized at 22, 23, 0, and 01. The traces are essentially a measure of the performance based on the fraction skill score. And essentially, the pink shading here represents where the data assimilated, or the model forecast from the data assimilated, was an improvement over the control, which did not have the torus data. And so you do see that there are areas where the model was improved. Now, there are areas where it wasn't. There were significant parts of this sequence where there was no improvement. In fact, there were some periods where it had a negative improvement. It did not improve the forecast. So this is perplexing. Why would assimilating data make the model worse? Nevertheless, we did see that. But by and large, assimilating these data improved the forecast. Now, if you exclude some of these data, so this is the data denial approach, and there's a lot here, but basic takeaway is that if the line is in positive territory, then it is improving, that layer is improving the forecast. So green here is surface data. So here we would see that the surface data is improving the forecast. Yellow is PBL, and the pink is the free atmosphere. And if you just kind of step back and look at this, there isn't one layer that's resoundingly, obviously, always improving the forecast. Obviously, at least my eye is drawn to 0Z, where we see surface and PBL having a significant improvement in the forecast, but you don't see that in every single initialization time. And so one of the takeaways here is that no one, at least for this case, no one observing layer was found to be consistently the most useful improving the ensemble analyses and forecast when assimilated. But in general, assimilating some of the data, or assimilating the data did improve the forecast. And it improved it because it improved the representation of convective cold pools, it reduced storm location errors, and more accurately depicted the inflow environment. Okay, so the other approach to this is not using real data. I don't know how many people are familiar with OSSI's observing system simulation experiments, but this is work that Sean Merdzek, Tara Ladwig, Eric James, and I are working on. A lot of this work I'm going to show is from the paper that Sean wrote recently. An OSSI is the way that you can assess the value of a new platform, data from a new platform, without actually having to operate the platform. So it is entirely in model world. All of the data are synthetic. The basic approach, this is from Sean and Tara's paper, is you start out with a nature run. Nature run is a high resolution kind of proxy surrogate for reality. So for our work, we're using a WRF simulation. You can see an example over here. High resolution, 1 kilometer, CONUS scale. So this is not just focusing on severe storms, it's focusing on everything across CONUS during these 2 weeks. So first week was in April and May, second week was in February. So we have a spring and a winter. So we take that nature run, and then we simulate conventional observation. So we actually take the positions of ASOS, the positions of radiosondes, positions of commercial aircraft, interpolate the nature run, which is all fake, but it is a high-resolution representation of reality, to those positions. And we do the same thing with UAS data. So we deploy UAS. Again, we're not actually flying. This is just artificial, but we place our UAS positions across CONUS. And then we take data from the nature run and interpolate it to these positions. And then we assimilate these data into an actual forecast model. And in this case, we're using a forecast model. We're using a variant of Rufus, the rapid refresh forecast system. That's since been changed to HER. So the results I'm going to show here from Rufus, our new results are going to be from the HER. But the idea is that that's an actual forecast model using GSI for data assimilation. And then we asked the question, how much did the new platform, in this case UAS, improve the forecast by using typical forecast verification? Okay, so for our experiments, and the experiments I'm going to show here, we're evaluating the density of UAS measurements. So we run a variety of densities ranging from 35 kilometers, so every 35 kilometers is a drone, up to 300 kilometers. This is a lot of drones, 6,335 drones, and that is what they would look like. That'd be really cool if we could actually do it. It is practically impossible, which is why we're doing this in an OSSI framework. But what we're trying to test is what happens when we go from 35 kilometers to 300 kilometers. How much does the improvement, if there is any, in the forecast change? The takeaway is that it improves the forecast. And not only improves the forecast, but it improves it a lot. So this is the percent difference in RMSE. So essentially the improvement in RMSE. We'll start with the analysis. The analysis improved with the 35 kilometer spacing by 40%, a 40% improvement in the accuracy of the model. That is tremendous. Now that's analysis. I mean, if you go to 6 hour, it goes to 20%, but that's still a pretty remarkable improvement. It's also a ridiculous number of drones. If you go to a coarser network, you still get a market improvement. So you can see that for the network of drones that is 300 kilometers, you still have about a 12% improvement at the 6 hours, and you see that both in spring and winter for the several state variables. So the takeaway is there's a big improvement. What's also interesting is that the amount of improvement per UAS is not constant. And so as you add more UAS, you don't actually get the same amount of improvement. For example, if we go from 20% to 30%, it requires 347 more UAS. So to get from a 20% improvement to a 30% improvement, we need 347. To go from 20 to 30, we need 1,000. To get 20%, we need 347. So 347 drones to get a 20% improvement. To go from 20 to 30, we need 1,000 more drones. To go from 30 to 40, we need nearly 5,000. So to get a 10% improvement at this density, we need 5,000 more drones. So we don't need that many drones to get a significant improvement, and adding more drones doesn't give a linear increase in performance. Okay, so summary, UAS significantly improved numerical weather prediction forecasts, at least theoretically. This is all theoretical, right? This is all synthetic. These are all based on nature runs, but theoretically they could offer a pretty significant improvement. The forecast improvement does saturate with increasing numbers of UAS. Okay, so this is an active project. We have additional experiments that are underway. What if UAS are limited by weather? That's one experiment. Actually, did I? I thought I might have included that. No, I didn't. If you're interested in that, I have some extra slides. What if UAS replace radiosondes? That's another experiment that's underway. What if UAS execute horizontal transects instead of profiles? Testing that as well. And the last one is, we've just started getting into this. This is a new project that was funded recently. What if we use UAS for targeted observation as opposed to kind of the surveillance observation? Okay, I went kind of long, apologies, but that's all I have. Happy to take any questions.
Okay, we have time for questions. That clock is actually a little bit fast, so you're only a couple minutes. Yep. I'm going to toss this gently.
It's padded. You can throw it.
Hi. I have a couple questions about the first two studies.
Yep.
Can you go back to the page with the boundary surges, like the?
Yeah, I'll just do this.
It's about the schematics. Not schematics, the actual temperature.
It's about this one or?
Down. It's about with measurements.
Yeah, I think I know. So that one. That one?
Yeah.
Okay.
Exactly.
Let me enlarge it.
I'm really interested in the low pressure part.
Yeah.
Can you talk more in depth about how do you think the low pressure is formed?
So our hypothesis is two possible explanations. One is because there's an SVC here, basically it's spinning above the surface, it's reducing the pressure through the fluid shear term. So essentially, because of this vorticity aloft, it's reducing the pressure in the column. The second possibility is because there's essentially a deep convective updraft above the boundaries, you essentially have a pressure reduction due to the buoyant pressure reduction.
So you think it's like both dynamic and buoyancy based?
Possibly. This, if it's tied to the SVC, it's dynamic. If it's tied to the deep convective updraft, it could be both. It could be both dynamic and buoyant, but it probably could be only buoyant. I don't know.
Okay. Thank you so much. And another question is go back to the Tipton storm. The one produced tornado. The other one didn't. There's here. The SRH, are you calculating it based on the actual storm movement, or is it some sort of like model movement or like bunkers movement?
It's a good question. Probably actual storm movement, but I can't be certain. Storm movement was not strongly actual storm motion wasn't strongly departing from the bunkers estimate. Okay. So I'm betting there's not a big difference. It's a good question. I'm pretty sure we did actual. If we go to the paper, we could find out for sure, but I don't know.
Okay. Can you talk more about the elongated hodograph you were talking about?
Yeah.
I didn't really get that part.
Yeah, that's right. Okay, so this is the hodograph from the environment ahead of the storm with the backed winds from the northeast. Essentially, we take the near surface point and bring it out here. So you've elongated the low levels of the hodograph. So if that's the surface observation, kind of southwesterly ahead, the northeast winds within the mat would cause that surface point to be way out here. So essentially the lowest level part of the hodograph would be elongated.
So that's so is that the difference, is it caused by the measurement, or is it just a difference in the ground-based storm motion?
The storm motion wouldn't be changing. So the storm motion would be the same, at least in theory. As you change the flow in the lowest levels, you could change the storm motion, but what we're saying is that even neglecting any change of storm motion, the absolute hodograph would be elongated because of the backed winds within the mat. Then you would basically put the storm motion somewhere on that hodograph and you can calculate the SRH.
Gotcha. Thank you so much.
Yeah.
Okay.
So in your RC experiment, did you check whether the winds or temperature or moisture were the most effect or had the biggest influence on the improvements?
We did not go into that detail. It's something we've talked about doing, looking at the specific contribution from those individual variables. We kept it pretty bulk. Yeah. It's a good question and something we've talked about doing.
It's right behind you. Oh, yeah, there you go.
Hiding right behind him. This was really interesting. Thank you. For the Aussies, I was curious. You showed kind of we can vary these UAVs over tens of kilometers to hundreds of meters. Did you happen to see, or did you get a chance to look at whether that improvement was concentrated in certain areas? So like, having 300-meter drone spacing or 3-kilometer drone spacing here made a big difference, but it didn't really matter over here.
Not yet. It is something we're talking about.
Okay.
It is a long list of what we want to do, but that's definitely one of them.
Okay.
Yeah, it's a really good question because it's unlikely that we're getting a uniform benefit. In fact, what surprised me in this result was how much the improvement was, considering that much of the environment was probably fairly either quiescent or not, frankly, improved a lot by UAS observations. So more likely than not, we're going to get these concentrated areas of significant improvement. We haven't really looked at that. And part of what we want to do in the second project is think about this kind of thing, targeting them where we need them the most, but I think that's probably something we need to pick off first.
Great talk. A quick question about the Aussie study that you mentioned. What is the drone doing there? Is it just moving at the same X, Y, and Z profile? Is it doing something fancy there?
Yeah, I didn't explain that. I should have, sorry. It's just doing a profile. So it's going from up to 2 kilometers AGL, just going up and down. Some of the other things that we want to test, number one, is what happens if it moves horizontally as opposed to vertically at a fixed height. And the other one is what if it does a deep tropospheric profile. So Alex, my student, is doing a set of experiments where he flies to 15 kilometers to see if that improves compared to somebody compared to 2 kilometers, so he's going to test that as well. But essentially, kind of as a replacement for radiosondes, there are reasons to suspect that they would be a better way of sampling the free troposphere than radiosondes, because what they can do that radiosondes can't is collect on the way down, right? So radiosondes, they go up, they're done. The UAS can go up and down, and then repeat, up, down, right? So you can get a higher temporal resolution, but also you get more of a complete profiling of the atmosphere over a fixed set of time.
Thank you.
You do miss the stratosphere if you can only go up to 15 kilometers, but.
Let's do maybe one more question.
Okay, thanks very much. How many humans were required per UAS in the air during your research study?
During the research, okay. I thought you meant during an Aussie.
Well,
that's easy, 0. But yeah, so this is a really good, sorry, I don't know if you finished your
well,
question.
the follow-up would be, if you kind of scaled that up to operationally using them, how would that number change?
Yeah, a lot. So in the scales experiment, we had 2 people for the sites that were out of the urban area, 3 inside, because we had to monitor more carefully the traffic. So even if we assume 2 per site, it's a lot of people. This is not a way to operationalize UAS. It has to be more automated. And this has been demonstrated. They have these systems set up where the aircraft goes up, it lands, it charges, it goes up, it lands, and so it's completely automated. Those systems do exist. There's only 1 or 2 of them. I mean, different types of systems. There's a lot of room to engineer that more efficiently. But yes, you will not have 2 people per site if you're doing a full deployment operationally.
Great, thank you.
Yeah.
Let's thank Adam one more time.